I've underlined, been asked for the limiting reactant. I've also been asked for the excess reactant, but obviously in this case, it would be whatever the other reactant is, the theoretical yield and the theoretical yield in grams. So I started with 10 grams of hydrogen gas. I'm going to multiply that by 1 mole of H2 is 2.016 grams. That acts to convert grams of H2 to moles. My stoichiometric ratio is 2 moles of water to 2 moles of hydrogen. I do have to put that factor in because with this factor, I am now in moles of hydrogen. I need to get to moles of water. So moles H2 cancels. And then I multiply that by the molar mass, 18.016 grams of water to 1 mole of water. And that gets me into grams. That tells me that I with 10 grams of hydrogen, I can form 89 grams, that's right, of water, H2O. So I'm going to do that with the oxygen. 1 mole of O2 is 32 grams O2. I will tell you that some of the most common math mistakes that students make, you're very used to using the molar mass of hydrogen is 1.008. That's true when you're calculating the molar mass of a compound, but when you don't forget to multiply those masses on the periodic table by 2 when you're dealing with the diatomic gas. So 1 mole of oxygen gas is 32 grams. And I get 2 moles of water for every 1 mole of O2. 18.016 grams of water to 1 mole. And I do like to just check and make sure grams of oxygen cancels, moles of oxygen cancels, moles of water cancels, and I end up with a mass. And in this case, I get 9.0 grams of water. Now remember that the smallest amount is the correct answer. That tells me that the limiting reactant here is the oxygen, and the excess reactant is the hydrogen. Can anybody tell me, based on the numbers I have here, how you could tell that that first reaction, that this has to be the excess reactant? Just looking at the numbers that we have.
This is more than the oxygen.
The moles?
Well, in this case, you could look at these numbers. They're nice and round. It takes 2 moles of hydrogen to 1 mole of oxygen, though. So we have masses, we don't have moles. You'd have to convert it to moles first. There's another simpler way of telling right off the bat. Once you've calculated all of these things out, there is a very simple way of seeing that this is the excess reactant. Any other ideas?
Would it be because it has to equal 100 and never mind.
Is it the mass of the substance? Like 10 grams and then 8 grams?
Absolutely, you're absolutely right, Chow. You're starting with, remember the law of conservation of matter? You have 10 grams of hydrogen and 18 grams of oxygen going into this reaction. Is it physically possible to get 89 grams out of that?
Yes.
Remember that the law of conservation of matter says that you cannot create or destroy mass. So if you start with a total of 18 grams of your reactants, you can't get any more than 18 grams on the product side. So 89 grams of water is absolutely impossible. You can't get 89 grams out of this reaction. So you could look at this and see from that, you could tell that this is probably the limiting reactant. But it also, we said that it's the one that produces the least amount of product. Did you have a question, Rowan?
I have a question real
Sure.
quick.
Sure.
So you're saying that it would be impossible to have more than 18.016 grams of water?
It would be impossible to have more than 18 grams on the product side. Yes,
Okay. And
absolutely.
that's like just a little trick.
Yeah. And it's in this case, the numbers are such that you can look at it. And I mean, actually, when I worked this problem out and I looked at that and I said, 89 grams, wait a minute, that's nuts. You can't possibly have that amount of product. It is what you would calculate starting with 10 grams of hydrogen, but it is an impossible amount given that you've only put in 18 grams of reactants. Now, based on that, how much, the other question is, how much of the excess reactant would I have left? This is my theoretical yield, by the way, in grams, which is what I was asked. But based on that and based on this discussion we've just had, can I determine how much hydrogen is left over?
Would it be 9 grams of hydrogen?
Tell us what your thinking is.
So if we start off with 8 grams of oxygen and then we end up with 9 grams of H2O, that only leaves 1 gram left over for the other element.
We have 18 grams of reactants, right? We have 18 grams that we put in, 10 plus 8. We have produced 9 grams of water. What else is there? Water was our only product.
So hydrogen would be left over, 9 grams of
Hydrogen is the only thing that's left over. So you have 9, you have to have 18 grams on both sides. You have 18 grams of reactants, you have 9 grams of product. So you must have 9 grams hydrogen left unreacted. Now we could go through a mathematical exercise that would calculate how many moles of oxygen we have, how many moles of hydrogen that would react with. That would tell us how many moles of hydrogen are used. And the balance of the oxygen would be unused, and that would be represented by 9 grams of hydrogen. So we could go through a mathematical exercise calculating how many moles of hydrogen are used and how many moles of hydrogen are left over. But in this case, we really don't have to, because we know that we started with 18 reactants, we formed 9 grams of product, we must have 9 grams of hydrogen left over. Any other questions on that? Can I what?
Can you scroll up a little bit? Can you
Scroll
go up
up?
a little bit on the problem?
On the problem? Sure.
Yeah. Thank you.
Is that what the questions might look like on the test, where we have to find everything, like the limiting reactant, the excess?
Yes. I'm going to do another problem or two with you guys today. And then I'm going to let you guys practice. I'll give you some instructions when I put you in breakout rooms. We have a lot of practice problems. I don't know that we'll get through all of them today, but they are on the PowerPoint, and the PowerPoint is posted. So any that we don't get to, you can certainly practice with. These kinds of questions can be asked in hundreds of different ways. And so I'm going to try to give you some examples of how they could be asked so that you can get a sense of, they really are the exact same problem. They may look different because you're given slightly different information, but they all are essentially the same. Now, is everybody finished with this? Can I go back to my screen share?
Yes.
I'm not hearing an objection, so we will go back to the screen share. So there was my last question. How can you determine the mass of excess reactant left over? So here is another sample problem. I'm going to do this one for you, and then I'm going to put you in a breakout session where you can practice one. So I've asked 4 different questions on this. The problem is magnesium chloride aqueous is mixed with sodium hydroxide aqueous, and the products are a solid magnesium hydroxide and aqueous sodium chloride. Now notice that I have been given a mass, even though this is aqueous, I have been given a mass. I could be given a volume and a molarity. If I gave you volume and molarity, you could figure out moles from that, and that would tell you the moles of magnesium chloride added. But in this case, I've told you mass. You can assume that that is 16 grams in whatever volume of magnesium chloride was added. And you will see that I have added it to 1 molar sodium hydroxide. So I'm going to go back to my my thing is so sensitive. I'm going to go back to my camera share in a moment, but let's look at the questions and we'll answer them in stepwise. So how many moles of sodium chloride will you form from the reaction? So what is the theoretical yield of sodium chloride? That's one question. What mass of magnesium hydroxide will you form from the reaction? What mass of solid product can you collect? That's also a theoretical yield. How many moles of sodium hydroxide will you need to react with the magnesium chloride? So we're asking which of these 2 is in excess. What volume of sodium hydroxide solution will you need to react with the magnesium chloride? So those are the kinds of questions that you could be asked. So let's go through these one at a time. So I was given 16 grams of magnesium chloride and 1 molar sodium hydroxide. I'm not given an amount, I'm just told that it's 1 molar. So the first question asked for moles of NaCl. So 16 grams of magnesium chloride. Remember that the first step that you have to do whenever given a mass, this balanced equation is molar ratios, not mass ratios. The first thing that you have to do is convert that to moles. So I'm going to multiply this by 1 mole of MgCl2, and the molar mass of magnesium chloride is 95.21 grams. And that equals, gone from grams to moles, that equals 0.168 moles of magnesium chloride. And here's where I use my stoichiometric ratio. Haley, this was the question you asked before. It's 2 moles of NaCl to 1 mole of MgCl2. And so that equals 0.336 moles of NaCl. So that is how many moles of NaCl I get as a product. So the second question I asked there was how much, what mass, here I'm not asking moles, I'm asking for the mass of magnesium hydroxide. Remember from your solubility rules that hydroxide salts are generally insoluble. And this time I'm not going to start with the magnesium chloride. That's why I stopped here. I can start from the moles of magnesium chloride, 0.168 moles of MgCl2. And since they are 1-to-1 in this equation, go scroll up, they are 1-to-1 in this equation, then that equals the moles of magnesium hydroxide. Now all I have to do is multiply this by the molar mass of magnesium hydroxide, which is 58.33 grams per mole. And the mass ends up being 9.80 grams. I'm noticed that I started with 3 sig figs, so all of my answers here are in 3 sig figs. Okay, so the third question I was asked was how many moles of NaOH are required to react with that amount of magnesium chloride. So it's how many moles of sodium hydroxide are needed. And I can again start with 0.168 moles of MgCl2. And I need 2 moles of sodium hydroxide. For 1 mole of MgCl2. So I've now converted to that, and that is 0.336 moles of NaOH. Okay, so I've now, again, it's 3 sig figs. So that was my first answer, my second answer, and my third answer. The fourth thing I was asked, and this is where we can get into volume. So the fourth thing I was asked is the volume of NaOH needed, of the solution that's needed. So I'm going to write this as the question, how many, you can do this as liters or milliliters. It really doesn't matter as long as you use the right units on your conversion factor. So I can ask how many liters of NaOH equals 0.336 moles of NaOH. The relationship I was given in the problem was it was 1.0 molar. So I know that my conversion factor here is going to be 1.0 liters is 1.0 moles. So that tells me I'm going to need 0.336 liters. This time I probably should change that to 2 sig figs. So it would be about 0.34 liters. If I do it in milliliters, I could ask the question, how many milliliters NaOH are required? It would be exactly the same, except my conversion factor here would be 1,000 milliliters is 1.0 moles. Everything else is the same. And this would give you the answer in milliliters, or 336 milliliters. Again, to 2 sig figs, it's about 340 milliliters. So you can do it either way. It doesn't really matter. When you're asked a volume, unless I specify that the volume should be in one unit over another, you can do it in whatever one makes sense for you. Okay, so there is a, oops, sorry, I didn't mean to do that. There is a discussion that gives you a problem that has 4 steps like this. I am going to put you in breakout rooms. I'm going to put you into I'm going to put you into breakout rooms. Hopefully that there'll be about 4 of you in each. And I'd like you to work together for this. I'm going to go around and check and see how you're doing. You can, I think there's 4 questions there. You can break it out so that one of you is each doing one part of the problem and then pool your answers and check them. By all means, work together. So I'm going to put you in breakout rooms and allow you, let's see, I think I'm going to have to make more. I'm going to add a room. Okay. I'm going to close that down because I had too many people in breakout rooms. So. Okay, now there's about 4 of you in each room. So go ahead and work together. And if you have questions, I'll poke around and see how you're doing. Nitrate equals 8 moles. The mass of sodium nitrate, the molar mass is 85.01 grams to 1 mole. So it's 680 grams of sodium nitrate. So I would need to decompose 680 grams of sodium nitrate in order to produce 4 moles or 128 grams of oxygen. Okay, so that's a slightly different way. It's still a very simple problem. It's just that I was not given the equation. I had to produce the equation and balance it. Simple enough to do, not that hard. So let's take a look. What else we have here? So that's basically working through that problem. Here's another practice problem. Hydrogen is produced by the reaction of 118.5 milliliters of a 0.8775 molar solution of phosphoric acid, according to the following equation. It's clearly balanced. So I would have to determine the moles of hydrogen gas formed. I've been asked for that. Determine the mass of chromium 3 phosphate formed. Determine the mass of chromium that will react with the acid. And in the final question, I've been asked, at room temperature, a mole of gas occupies a volume of about 24 liters. Using this information, determine the volume of hydrogen gas produced. So it's essentially the same kind of a problem, except this time I'm starting with a volume and a molarity to determine the number of moles. So I wasn't given a mass. I was given the volume and molarity, and from that, I'm going to get the number of moles of phosphoric acid that goes into this reaction, and then determine how much hydrogen is formed, etc. Any questions on this? Do you want me to go through this problem, or do you want to work on it yourself? More you do them. I've been doing these problems for 20 years. I know how to solve them. You guys need more practice than I do. I'm happy to do it if you want, but I'm also happy to leave it on the PowerPoint and let you practice. So give me some guidance.
Can you do it?
I
Can
just
you
want to
do
make
it for
sure
us?
that I have the answer. So if I do it, I see where I didn't do it. Right.
Okay, I was just asked, can I do it? I just want to
Yes,
say
please.
that's probably a silly question. I think I can do it. I think I can. So,
I don't think you can do it.
is that a dare?
Yeah.
Okay.
I'm doubting you. Let's see it.
Okay. So I'm going to stop sharing my screen and I will go switch over to my other camera and do it. Trust me, you do these often enough, you can do them in your sleep. Okay. So there's my balanced equation. It's a reaction. Can anybody tell me, let's say I wrote here states. Can somebody tell me what the states would be for this reaction? Because they weren't written.
The first one is solid.
That's right. So chromium solid, it's the metal. Yep.
The second one is aqueous.
Yep.
The other one is gas.
Hydrogen is a gas. Yep.
The last one is solid or aqueous.
It,
Oh,
it,
solid?
it is a solid. It is a solid.
Yeah.
Absolutely. Phosphate salts are insoluble. Okay.
All right.
So absolutely. Good job, Oyaluwa. I know you've been practicing. Okay, so I was given a volume and a molarity. So let me write the question. The question is, how many moles of H2 equals 0.1185 liters? It was 118.5 milliliters, so I converted that to liters, times 0.8775 moles per liter. So that is the molarity of the solution. Note that I was given both of these numbers in 4 digits. So my answer is going to have 4 significant digits. To that end, I am going to carry an extra digit and then round at the end. So I'm going to carry an extra digit here. When I do this math, I end up with 0.10398 moles of phosphoric acid. And I have 3 moles of H2 per mole, 2 moles of H3PO4. So it's 3 to 2. So when I do that math, I end up with 0.15597 moles of H2. But I'm going to round that to my final answer is going to be 0.1560 moles of H2 when I round to 4 significant digits. Okay. All right, the next one is determine the mass of chromium 3-phosphate formed. Well, I'm going to start with the moles I get of phosphoric acid. So I had, I'm asking how many grams of CrPO4 equals 0.10398 moles of H3PO4. And the ratio for my balanced chemical equation is 2 to 2. So you could say that they are 1 to 1, or you could simply multiply this by 2 moles of CrPO4 to 2 moles of H3PO4. And then I want an answer in grams. This is going to give me moles. I need to multiply that by the molar mass. The molar mass of chromium phosphate, when you calculate it, is 146.97 grams of chromium 3-phosphate to 1 mole. And when I do that math, I'm going to end up with 15.28 grams of chromium 3-phosphate.
Excuse me?
Yeah.
Where do you get 0.10389?
I got that from here. When I calculated the volume times molarity, I figured out how many moles of phosphoric acid were put in this reaction. So I'm going to carry that through. I'm going to use this. This is the only amount that I was given. I was given 118.5 milliliters times 0.8775 moles per liter, or 0.8775 molarity phosphoric acid. So that's the only amount that's given, and I have to base everything off of this.
I see it. Thank you.
Okay. All right. So the next question is determine the mass of chromium that will react with the acid. So how many grams of chromium? It's the same number of moles, equals 0.10398 moles. Notice that I am taking 5 digits all the way through and then rounding at the end in each case. So this is H3PO4. And this time it is 2 to 2. So 2 moles of chromium to 2 moles of H3PO4. That's going to go from moles of H3PO4 to moles of chromium, but I'm going to have to multiply that by the molar mass, which is 52 grams chromium per mole. And that mass then is 5.407 grams of chromium, 4 sig figs. Now, the last question is a little bit different. We said that we could use density or to get volume or something like that. In this case, this is a relationship. We're going to do gases next chapter, but this is a relationship that you could calculate once you've learned a little bit about gases. But the question is, what volume of hydrogen is produced? So I want to convert the, so how many liters of hydrogen gas equal the number of moles? And if you remember, the moles of hydrogen was 0.1560. Now I can use this 0.15597 and then do the math. It really isn't going to matter if you choose to use that, or you choose to use 1560, which was the one to the correct number of significant digits. Your answer will be different by maybe 1 or 2 in the final decimal place. It's really not going to matter, but it's 0.1560 moles of hydrogen. And what I know is that 1 mole of gas at room temperature occupies about 24 liters. So I can multiply this by 24 liters per 1 mole. And that converts and that's 1 mole of any gas. So that converts my moles of hydrogen into volume. And this time, because I only have 2 significant digits here, I'm going to have to round this to 2 significant digits. So it is 3.7 liters. Because I'm rounding this all the way down to 2 significant digits, that's why it probably doesn't really matter whether you use the 5 digits here or whether you use the 4 digits. You're still going to have to round to 2 at the end. So the answer will essentially be the same. Any other questions? See, I told you I could do it. Okay. There are, class is over. There are other problems up there. In the PowerPoint, we're going to be starting to do, I think there's some slides that show practice problems, and then we get into some other gravimetric analysis and things like that. So I think there's a couple more slides of problems you can certainly practice with if you need to. Okay.
I see the last part.
You
I
want
didn't finish.
to see that last problem again?
Yeah, I didn't finish copying these. Okay, there it is. Okay, thank you. Is this problem going to be on the PowerPoints?
I'm sorry?
Is this problem on the PowerPoint?
That problem is on the PowerPoint. And let me, I will actually share my screen and I will show you that there's a, so this is that problem that I just did. There is,
Hold on.
there is, this one has two. You have to write the balanced chemical equation in this case for both of these. And here's another practice problem. There's two more practice problems there. So there's 4 practice problems. Here's where you can stop. Stoichiometry and quantitative analysis. We will do this on Thursday, but there are 2 more slides with 2 practice problems on each. You can work on those. And between all of these, you've probably seen pretty much any way that the problems could be addressed or asked.
Okay.
Okay? So
Excuse me, Professor. I'm sorry.
look at the very least, you should look at them and see if you can ascertain how you would go about addressing them. How would you approach them? And as long as you have an idea of where you would go and what you would do, that's what you need to do. Yes, Chow, you had a question?
I just want to confirm that next class we're gonna finish up chapter 7, and then we have a quiz.
You have a quiz only on the material that we did. None of the material today. This is stoichiometry. None of the material today. It's identifying what reaction type it is, redox, non-redox, metathesis, synthesis, etc. Those kinds of things. Oxidation states, determining oxidation states. Anything that we did in the first 2 sessions on chapter 7. This is our 3rd. Anything that we did last week on chapter 7 will be on the quiz. I think there's 4 problems. And as I said, there's no work upload this time.
Okay. And then next week that we're gonna go over chapter 8, and then we have an exam on Thursday.
Yes.
Are you gonna talk more about the exam or no?
I could probably talk about the exam on Tuesday. I'll give you a little bit of guidance because I'm going to write it. I will have it written by the end of the weekend. So I will have it written by next week and I'll be able to tell you a little bit more about that. As I said, I fell behind. I was working on some questions on the test bank and I fell behind on labs. So I'm trying to get the labs graded, all the labs that you've done graded by the end of this week. And then over the weekend, I will work on the test so that I can tell you on Tuesday what it'll look like.
Okay, that's perfect. Thank you.
Awesome.
Thank you, Professor.
Thank you. Have a great day. We'll see some of you tomorrow for lab.
Bye.
Bye, Professor.